Good morning, Zoomers. Mel Boynton here, and we're going to be starting in about 4 minutes. We appreciate your keeping your microphones muted. Later on, we'll be taking questions. You'll raise your hand, so be sure to have your video on when the questions come. We're glad you're here. See you in a couple minutes. Morning, everybody.
Good morning. Hi. I'm good. How are you, Mel?
Good. Good morning, Carly.
We heard you before.
Oh, fantastic. This might not be so dissimilar to what you.
It was great.
Yeah, thank you.
Later a bit, so I'll start here. Michael is our social media editor. There's a coffee table. Oh, thanks. I think you saw the lineup.
That's fantastic.
It's really good. Still got a lot of.
All my family's
All. Or they think about you being stuck in Southern California.
They are sad right to move because but they also love to winter. So
Yeah.
I think they prefer.
Okay. Well, you're making lemonade. Yeah, that's great.
And we're lucky to be in the era of FaceTime and Skype
Yeah.
and stuff.
I'm gonna stop this share for now. I'm gonna go to. Okay, looks like we're defaulted to gallery view, which is good. And we'll do a little sound check with the Zoomers, make sure they can hear. And we do have hard of hearing.
Okay.
It's we're a diverse congregation, but we got a lot of gray hair, so
Yeah.
nice and loud today.
Oh, also, sorry.
Yeah, it's California.
Yeah.
You're not the only one to do that.
Kick us off, Jake?
No, please go ahead.
Okay. All right.
Thanks, Mel.
Sure.
Yeah, this is this.
That's what I was looking for. I was looking for a full thing. Good morning, everyone. People on Zoom, could you give me a thumbs up if you can hear us? I think we're live.
I was just telling Dr. Brown we can get started like 9:02.
9:02?
People show up here between 9
Oh,
and
okay.
10. So if you wanna
I'll
go
make that, we'll start in 2 minutes. That's good. Thank you. Sorry. We had multiple cameras. We would. When we were presenting, also the slideshow.
So I'm actually gonna face this way, so I actually put it on an angle so that I'm not hiding behind. So you'll be looking toward everybody. That's my plan. Yeah. Yeah.
You know, I like the international third one. That's why I'm wondering about that. We're watching more.
For this, I think I would leave it up to the presenter. So I don't like to provide something with technology because then I find it like the barrier between me and the audience. So that was I'm the one that took it this way, but my plan is yeah. But if you do have trouble hearing me, okay, good. Just flag me though.
We'll try this one more time. Good morning, everyone. My name is Mel Boynton, and I'm on the Arts and Education Board here at the church, and we've put together a wonderful April series on environmental action and justice. I am so glad to see a good turnout this morning and being joined by our people on Zoom and Instagram this morning. So it's my pleasure to introduce our leadoff speaker. She's just terrific. You're going to find that in a second. Branwen Williams. Dr. Branwen Williams is the George R. Roberts Professor of Integrated Sciences at the Environmental Science at Claremont McKenna College and Director of the Roberts Environmental Center. Her research explores interactions between our environment and human activities. To do this, she develops and interprets records of environmental variability in our oceans, from the tropics to the poles. She also works with local communities to help build resilience to climate change. That's the focus of the presentation today. Branwen received her Bachelor of Science from the University of Guelph and her Master's of Science from the University of Quebec. I understand those are in Canada, where she still has a lot of family. And she also has her Ph.D. from the Ohio State University. I have family in Columbus, Ohio. She is a National Geographic Explorer, and her research is funded by the National Science Foundation, the National Oceanic and Atmospheric Administration, and the Henry Luce Foundation. Welcome, Dr. Branwen Williams. I think so, yeah.
Good morning, everyone. We are just navigating Zoom so that you'll be able to see some of my figures. I am a scientist, so I do like to show some data. And then Mel, can we put the slideshow up too? Otherwise, it really will be a talk of a lot of hand waving.
Well, we'll have.
There we go.
There we go. And share. Great. Do you have embedded video?
I have one. It worked when I checked it
Okay.
earlier. So
Good.
it should be fine.
All right. Great.
So, fingers crossed.
Nice.
Okay. Good morning, everyone. Thank you so much for coming to spend this time with me. It's been a beautiful day out. I asked Mel for parking when I was in touch with him earlier this week. To this one? Okay, how's that? You're good. And I was able to ride my bike today just because the weather is so lovely. We're very fortunate to live in Claremont. I was invited to talk a little bit about what I think about in terms of our environment and climate. And I actually started hearing about climate change when I was an undergraduate, which as a college professor now, working with so many of our students, was such a special time in our lives. And that means it's been a few years that I've been thinking even closer, louder. Or maybe how about I move this closer to me here? Does that work? Okay. And then can we, or the Zoom, can they still see? Okay.
They're hearing you loud.
Okay, perfect. But please do flag me if you have trouble hearing me at all. The Canadian accent might get annoying. And so we're going to talk today about climate change, and I'm going to present it in the kind of the framework that I think about it. And about 2017, 2018, I realized that we had kind of missed the boat in solving climate change. And now we need to think about what are we going to do about it. And I really shifted my focus to starting to work with communities and thinking about solving climate change in a different way. How do we build resiliency to what's happening on our planet? I'm going to start by telling a story. And I heard this story when I was on a run listening to a Freakonomics podcast. One of the things that I get to do as a climate scientist is time travel. So right now we're going to go back in time to about the early 1900s into New York City. And if you look at this, you can see a lot of people moving around, and they're walking and they're using horses and buggy. So back in the early 1900s, horses was one of the primary modes of transportation that people used to get around. And there started to become a problem because with horses, they eat food, which gives them their fuel. They use that fuel to generate energy, which causes them to move, but not all the food is consumed. There's also waste products. And those waste products were building up on the streets of New York City because of all the horses and all the people wanting to move. So a solution was proposed. Let's try this new type of transportation, which doesn't require food and doesn't produce the same waste products. And so there was a push to shift from using horse and buggy to get around to using cars. Cars don't eat food, but they still use fuel. They take the fuel that we put into them, our gasoline. They use chemical reactions to get energy from the gasoline, but they still have waste products. We don't see it unless you think about the smoke coming out of a car, but it's putting gases into the atmosphere. And the same way that when you have a lot of horse waste products going on the street, there's unfortunate consequences. Burning of cars or burning of fossil fuels with cars also has unfortunate consequences. Putting that gas up into the atmosphere is now harming our planet. And we're at the point now where it's causing harm to people. Of course, our cars these days don't look like this anymore. Now we look a lot more like this. And the number of cars in the road has only increased exponentially. The size of cars is getting bigger and the number of cars around the world. So today we're going to talk about the implications of that waste product going up into the atmosphere, carbon dioxide primarily, and then what we can do to build resiliency to the changes that it's causing. I think a lot about temperature, probably more than most people. This is a map of how temperature has changed over the last 150 years, going back to 1880. You can see that temperatures are kind of fluctuating. They're warming up. We're now at 1960s. Blue is cooler temperatures, red is warmer temperatures. There's a lot of variability. But starting the late 1970s, temperatures really started to warm. One of the things I want you to get from this talk is our planet is dynamic. It changes all the time without people's influence. But the changes we're causing now dwarf that natural variability of how our climate system changes. 2023 was the warmest year on record. On record means so however long we've been keeping instrumental records, which goes back to about 1850, and it's going to continue to warm. But that warming is not equal. It varies depending on where you live. If you're closer to the ocean or inland, we all know intuitively that Palm Springs is a lot hotter than Santa Monica. It depends on if you're in the poles or if you're in the tropics. Depends on if you have a lot of tree cover or not. And it's going to vary a lot where you are through time. So some places have actually been a little bit cooler, other places have been warmer. But on average, our planet is warmer than we've seen. So who am I up here to talk to you about climate change? I think a lot about, as Mel said in the introduction, how our environment changes naturally before human or without human influence. And then what are humans doing to change that variability? To do this, I go to places where people don't normally go to get records of environmental change. So this is me standing up on top of the ocean. I'm above about 400 meters of ocean water standing on the sea ice in the Canadian Arctic in July, so right after the longest day of the year. It's July, but I'm actually wearing all my layers. And if I had come back a week later, that ice would have been melted and I would have been swimming in the ocean. If you look at the bottom right of the picture, you can see the start of the summer melt pool. So this is an example again of how our world is really dynamic. So from ice covering the ocean to no ice there within a week or two during the summer season. I was up here because I wanted to collect data of how the sea ice and the ocean temperatures are changing. Sea ice, ice cover is a really important part of our climate system. The way I do this is I get data from climate archives. So this is a picture of an algae. An algae is a plant, but it forms, this specific type forms this rock skeleton. So you can see a rock hammer, because I'm a geologist, so I have to use a rock hammer for scale. That entire object behind the rock hammer is the hard skeleton that this algae forms. The pink is the living tissue layer. Now, this is the biggest one we've ever collected, so we like to show it in photos, but it was about this big. And in that skeleton, it's captured and stored information about the environment while it's been living. And we can get that information from it and tell us about past environmental variability. So an analogy is trees. Maybe it's intuitive to think about if you cut a tree at a tree trunk and it has the growth rings in it. There's a wonderful example at our local California Botanical Gardens, a huge tree trunk on its side like this. And that tree grew for about 2,000 years. And in it, they've noted significant events in the past. So this algae does the same thing. We can cut the skeleton across in sections from the oldest part of that skeleton when it first started growing up until the modern part where that pink living tissue layer is. And it has growth rings in the skeleton, just like a tree. And in this algae, it's going to grow more each year when it's warmer and when there's more sunlight reaching the seafloor. And it grows less when it's cooler and there's less sunlight. So in the Arctic Ocean, when we extract from this type of algae how much it's grown each year, it can tell us how warm the ocean is and how much sea ice there is. And the cool thing about these algae, they can grow for hundreds of years. So now in the Arctic, we have hundreds of years records of sea ice variability and temperature variability to understand how the Arctic Ocean is changing. Now, I think about fairly short timescales, kind of an environmental historian, but not of people, of the environment. But some of my colleagues think about changes on much longer time periods. So this is an example of people who go down to Antarctica, where there's layers of ice, and they go collect what we call an ice core, and they can extract environmental information from those layers in the ice. So we're going to start our time traveling now, going even further back into time. I did promise you data, so I'll show you a couple data slides. In these slides, what we're looking at is across the bottom, from left to right, we're going from 800,000 years ago to the present in time. And then on the y-axis, which is the vertical axis, going from the bottom of the screen to the top, is carbon dioxide concentrations in the atmosphere in parts per million. So these scientists, they go down to the ice, they collect these ice cores, and they can measure bubbles that are trapped in the ice. And the composition of gases in that bubble represents the concentration of gases in the atmosphere when that ice was formed. So we can trace carbon dioxide in the atmosphere going back the past 800,000 years. And what we can see is that it varies a lot. During colder periods, ice periods, it goes down to maybe 160, 180 parts per million. And during warmer periods, we call those interglacials, like the one that we've been living in, it goes up to as much as 280 or 300 parts per million. Now, we've been putting carbon dioxide into the atmosphere. Does anybody know what concentrations we have about in the atmosphere right now? Almost, not quite. We're just above 400. We'll get there soon enough. But this gives you an idea of how much carbon dioxide, that waste gas from burning fossil fuels, we've put into the atmosphere, and how different it is from that natural variability in our climate system. Now, some of you might say, well, 400 parts per million, that's not a lot. Think about it. If you had 1 million golf balls and they're all white except for 400 and they're yellow, that's not a lot. But it turns out some things are actually pretty dangerous in small amounts. Arsenic, for example, can cause harm in these concentrations. So what we can do is we can take that last little period of time and let's zoom in on it. So instead of going back 800,000 years, let's just go back to 1850. This is the time period where we have our instrumental temperatures when thermometers were invented. And then we can also look at how carbon dioxide has changed in the atmosphere. So now across the bottom, we're going from 1850 to 2023. On the left vertical axis is a change in temperature from the 20th century average. And on the y-axis on the right, the vertical axis, is the change in carbon dioxide. So much shorter time period, and you can see that they both go up together. This really shows that global warming that we've seen in the past 50, 60 years, since kind of the 1960s, 1970s, and carbon dioxide has gone up the same lockstep. Now, just because two things change together doesn't mean one causes the other. A scientist likes to joke that correlation, two things changing together, does not mean causation. One is causing the other to change. But here, we actually have a really great understanding of the mechanism. And in fact, we've known this for a very, very long period in time. There's a paper presented at the American Journal of Science and Arts in 1856, just a few years ago, that highlighted the role of carbon dioxide in controlling the temperature of our planet. And for all you feminists out there, it was presented by a female scientist. So the mechanism is our greenhouse gas. And I'm sure all of you heard about the greenhouse gas effect. We have our planet, and think of it as a nice thick wool blanket around our planet. This blanket has very special properties. It lets UV and visible light come through the blanket. We know that we get light we can see, and we know we have UV that comes into our planet. That's why we should wear sunscreen. Your PSA announcement, make sure to wear sunscreen. And what happens is it comes into our planet, and some of it, when it hits our Earth, is immediately reflected and goes back up into space, and it doesn't cause a lot of warming. Some of it comes in, it hits our Earth, and it's absorbed, and it warms our planet. And it's then released back up into space, but it's a little lower energy. It's called infrared radiation. That infrared radiation, because it's a different property than the incoming energy, actually gets captured by that blanket. And it stays in our system and it warms. Only some of it leaves. And really, thank goodness for that blanket, for those greenhouse gases, because if we didn't have them, our planet would be really, really, really cold. And I say that as a Canadian. So greenhouse gases on themselves, by themselves, are not bad. They are, and they have let our planet be inhabited. But what's happening is we are adding layers to that blanket, and we are making it thicker by increasing the concentration of carbon dioxide in the atmosphere. So that the same amount of energy can come in. It varies a little bit depending on what the sun's doing, but on average, about the same amount of energy is coming in, but less is leaving. Because that blanket is thicker, it's getting captured, and it is warming our planet. So that excess waste products from our automobiles, from our other burning of fossil fuels, is making that blanket thicker, and it's keeping the energy in our system. It's causing warming. So this paper in 1856, as far as I can tell, was the first time somebody really articulated that carbon dioxide can serve, they didn't use the word greenhouse gas, but can be a greenhouse gas. But we've actually known since at least 1966 that people putting carbon dioxide into the atmosphere can cause warming. And this is from Glenn T. Seberg, and he said, 1966, again, at the rate we are currently adding carbon dioxide to our atmosphere, within the next few decades, the heat balance of that atmosphere could be altered enough to produce marked changes in the climate. And then by 1988, scientists were already testifying in front of Congress that global warming has begun. So this science is sound. We've known it for a very, very long time. And I sometimes think about it, if we had dealt with it then, I wouldn't have a job. An analogy is Y2K. Does anyone remember Y2K? So late 1990s, we're all worried about what would happen when the turn of the century, when the numbers flipped from 99 to 2000, and everything would fall apart, and we would lose all our money in the banking system, and chaos would ensue. What did we do? We hired a lot of people, they went in, they fixed the problem. The year 2000 started, and nothing happened. That could have been climate change. We could have solved it at that point in time, and we wouldn't be dealing with it now. So our inaction has created the problem. So now we're going to go back even further into time. We're going to go back to 65 million years ago. So across the axis, I'm not showing you the data quite yet, we go from 67 million years to present. Our y-axis, the vertical axis on the left, is the mean temperature difference relative to today. And if you look at those range in values, they're huge. We're going from -7 degrees Fahrenheit up to 36 degrees Fahrenheit. On the right, you can see some blue squiggles, and that's going to include that last million years of ice core data that I showed you already. I think about it, again, my timescales are like barely in that blip on the far right-hand side. And I'm also going to show you ice sheet extent. SH is Southern Hemisphere, so that's our Antarctica ice sheet, and NH is Northern Hemisphere, which is Greenland, but during those glacial periods is also part of North America was covered in ice sheets. Is anybody from the Northeast? A few people, a little bit, okay. So I like to pick on Boston, that's where my in-laws are. Boston, during that last glacial period, about 20,000 years ago, was under ice sheet that was a couple of miles thick. Huge, huge amounts of ice. So let's see, how has temperature changed going back this period in time? Well, it's changed a lot. If we go back 65 million years ago, that's right at the extinction of the dinosaurs. So we know that an asteroid or meteorite came down, hit the planet, caused massive climate change, dinosaurs were extinct. And then since then, our planet warmed a little bit, up to like 12, 16 degrees warmer than today. So if anybody tells you the climate's been warmer in the past, they're right.
It's been a lot warmer in the past. And then slowly it cooled. And it cooled because of chemical reactions, took the gases out of the atmosphere, and they buried them into rocks and they put it into the deep ocean. Also, living things during this warmer and wetter period, there's a lot of bigger organisms and more primary productivity, so more photosynthesis, more plants. Those things died, they got buried. As they got buried, they got things layered on top of them. The temperature went up and there was more pressure on top of them, and they slowly converted through chemical reactions into fossil fuels that we're burning now and putting back up into the atmosphere. So that started that cooling. And then just after 35 million years ago, we started getting the formation of a solid ice sheet on East Antarctica. And you can see there was a rapid drop in temperatures. I went back to when I talked about the Arctic, about how important ice is. That's because it changes the energy balance of our system. When energy comes into our system, and I said some of it was reflected and some of it's absorbed, it depends a little bit on what that surface is. If that energy coming into our system hits ice, ice is really reflective, and it will actually more likely go back out into the atmosphere and into space. If you melt the ice and reveal blue ocean underneath it, the blue ocean actually absorbs that energy coming in and causes warming. So in this case, with the cooling, what happened is temperatures were cooling because greenhouse gases were being pulled out of the atmosphere. As temperatures cooled, you started getting the formation of ice in Antarctica. That reflected more energy, which cooled temperatures, which let more ice form, which increased the reflectivity, which put more energy back into space, which caused cooling, which caused more ice to form. And we call these feedbacks. And they can take small changes in the climate system and cause rapid, major results. So with Antarctica, the glaciation in East Antarctica, you can see there's a cooling around West Antarctica, and then also when those Northern Hemisphere ice sheets occurred. So these are one of our climate system parameters that has a big response, and that's why I was up in the Arctic to try to understand how the Arctic is changing. Now, this is really cool that we can look at how our climate has changed on long timescales. And climate scientists have a pretty good idea of all the things that are involved in causing these temperatures to change. And what we know is that what's happening right now, none of these variables explain it. The only thing that explains it is humans putting fossil fuels up into the atmosphere. The other thing that's really cool is we've categorized these periods of past climate change. Right now, we're actually in an ice house climate because we have those Northern Hemisphere ice sheets and Antarctica ice sheet. Back when there was just ice on Antarctica, temperatures were a bit warmer. They were about 4 degrees Celsius warmer. And that was a cool house climate. Then we go further back in time into when we had our warm house climates, when temperatures were 8 to 10 degrees warmer than today. There was no ice. And then we have our hot house climate, back when temperatures were 12 degrees, 14 degrees warmer than today. So the other thing with time travel as a climate scientist, we get to go into the future as well. To do this, we use our climate models. So climate models are using physical equations, numbers, to represent parameters in our Earth system. What I'm showing you here is we're going from 1850 on the left to 2100 on the right. I'm not showing you the future data yet. The black is the instrumental data that we've looked at several times now. And the purple is the range in values that the models give us. And this is a set of about 40 models from international scientists, different groups working. So it's not just us, it's many, many different groups all working individually and the results combined. And you can see the models capture that historical variability pretty well. I have a lot of confidence in our models. So now let's time travel into the future to see what our climate is going to look like by the end of this century. What you'll see is there's a range in variables. We have 4 different pathways. And what it comes down to is it's not what the climate models of the system tells us of what climate's going to be in the future. It depends on what people do. That determines our future. The largest variability, or driver of variability of our future climate is the choices we make. So these 4 pathways are called the shared social economic pathways that social scientists have devised of how humans might continue making decisions. The top right one, the yellow, is the intensive fossil fuel future. We've actually largely avoided this. We're probably not going to go down that pathway unless something happens or we make some really bad decisions. So we've probably already avoided this future. The sustainable future, the bottom purple one, we also probably have missed this one. It's probably not going to happen. We would have had to start a couple of years ago, more than that, to really reduce our fossil fuel use. We're probably going to avoid, unfortunately, the sustainable future. So we're somewhere in between the other two. Part of the reason I present that kind of perspective of how climate has changed in the past is we can use that as an analogy for the implications of what might happen going forwards. So we can think about our future climates, depending on the sustainable future, the fossil fuel future, and somewhere in between. Something to point out is that the climate doesn't actually end in 2100. So let's consider what might happen after that as well. If we had done that sustainable future, we would have kept temperatures about where they are today, somewhere, in between cool house, maybe warming up a little bit. If we had done that fossil fuel intensive future, we would have gone towards that warm house, hot house climate. And if you remember that hot house climate, there was no ice on Antarctica. That was the future that we had in front of us if we had continued burning fossil fuels the way we are. Right now, if you look at all of the international commitments to reducing carbon dioxide emissions, we're going towards a 5-degree Fahrenheit warming, which puts us somewhere between on that warm house climate. Not by the year 2100, but maybe shortly after, there's a possibility the Greenland ice sheet would melt. Greenland ice sheet, if you melt it, would increase sea level rise about 7 or 8 meters. Multiply that, maybe about 20 feet. The world's population, about 8% of the world's population would be underwater, and another couple percent would be vulnerable to severe storms and flooding. Those people would have nowhere to live. So that is the future that we are on track for right now. Maybe not in the next 10 or 20 years, we can say that for certainty, but if we roll the world forwards another 100 years, 200 years. So this is where everyone kind of looks at me the way you are right now. You're not very impressed with me. Some of our students suffer from the climate blues, and they actually face apathy. But I'm actually really optimistic about climate change. I know it's a little bit weird to say that right now, and hopefully in the last 20 minutes of our time together, I'll be able to share with you why. So first of all, and I give this quote a lot because I find it really inspirational that we can do hard things. It's from John F. Kennedy in 1962. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard, because that goal will serve to organize and measure the best of our energies and skills, because that challenge is one that we are willing to accept, one they are unwilling to postpone, and one in which we intend to win. Now, do you remember what caused the mass extinction of the dinosaurs? An asteroid, meteorite came into Earth. So about 1.5 years ago, NASA actually did a test of our planetary defense system. There was an asteroid that was kind of coming, it wasn't going to hit Earth, but kind of coming close. And they sent a missile up into space, and they changed the trajectory of that asteroid. So I will point out that we now, as a society, have the ability to avoid having something from outer space hit our planet that caused a mass extinction of the dinosaurs. We can now do that. I would propose that we can also solve climate change, which is a human-caused problem. The other thing that I think is really important to point out is that we can do that, and it doesn't have to be at the cost of our quality of life. So now we're looking at changes through time from 1890 to 2021, and we're looking at the change in per capita, so per person, of carbon dioxide emissions and GDP in the US. And what you'll see is for less than a century, those two change together in lockstep. If we wanted to improve our quality of life, increase our GDP, then we had to use more fossil fuels to do it. But for a long time, since like the 1970s, those have been disconnected. Our CO2 per capita, so my carbon dioxide consumption and emissions, is actually probably less now than my parents or my grandparents. That is great news. We are on the right pathway. I'll point out that we have to get down to 0, but I think we'll do it. Now, sometimes people ask me, well, going to the moon was a US mission. Why do we have to reduce our carbon dioxide emissions? What about everyone else in the world? What about China? What about India? And that one is more kind of my personal moral obligation. If you look at who's put the carbon dioxide into the atmosphere, which has caused global warming, it's us. So this is looking at per capita carbon dioxide emissions, United States, and I put Canada up there too. Australia is up there. Our emissions per person have been far vastly above anyone else's. And I don't feel like I have that right to burn more fossil fuels than anyone else does. And so it is a moral obligation for me to reduce it, to let other countries be able to develop and to increase their quality of life so that they also can take up a bit of space. And if I have to minimize mine to do that, I'm okay with that. So how do we get there? So here's our pathway forwards. There's two things we need to do. First, we need to mitigate. How bad climate change gets depends on what we decide to do. We need to reduce our greenhouse gas emissions, and that will directly minimize temperature change. If we keep burning, and the longer we burn, the warmer it will get. As we start to slow down our burning, it will help reduce that warming. But the warming's happening, so we also have to adapt. To do that, we need to enhance resilience, and we need to reduce the vulnerabilities to climate impacts. And the last thing that I would point out with this is the implementation of it is one, we have to have action, and that needs to be economically feasible. It has to be socially just, and it has to draw from diverse stakeholders and experiences. I talked earlier about how climate change varies a lot by location. Despite climate change being a global issue, it is felt, it is experienced locally. And it is felt and experienced mostly by communities that have the least ability to do anything about it, and by the communities who are not the ones who are burning the most carbon dioxide. So we need to make sure that our solutions going forward do it in an equitable way and help bolster those communities first. When I think about mitigation to reduce our greenhouse gas emissions, we need to decarbonize. We need to take fossil fuels out of our energy system through an energy transformation. We need to do this by our 3 R's. They're a bit different than the ones I grew up with. Reduce, replace, and remove. Reduce, we need to increase our energy efficiency. This is kind of boring, a little bit dry, but we need to go into our buildings and we need to do all the retrofitting to reduce the amount of energy that we use. We also need to replace. We need to get to zero carbon energy sources. This graph shows clean hydrogen. I don't actually think any energy sources are clean, but they're definitely going to have less waste products. To do this, we need to go to electrification for low and medium temperature processes, which will be most of the ones that we use, and then hydrogen for high temperature processes. Finally, remove. We want to install carbon capture and storage technology to take the carbon out of the atmosphere that's already there, or if we continue to burn fossil fuels, to trap it before it can go up into the atmosphere. This one, from what I've seen, there's no viable strategies in place right now that work. There's a really lot of smart people around the world working on it right now, but nothing I've seen suggests that this is possible. So let's not cross our fingers and wait for that technology that does not exist. Let's start working on reducing and replacing in the meantime. We also need to adapt. And again, the adaptation needs to be done locally. And for this in California, I will always tell you about CalAdapt. This is a resource that's put together, led by the government, but also researchers, government agencies, industry stakeholders. And it's a way to assess how climate change is going to impact you. The two that we're going to focus on right now is temperatures and then also rainfall. Time, it's perfect. So when we think about warming temperatures, we want to think about the fact that changes in average temperatures maybe are not such a big deal, but changes in those extreme temperatures are what causes impacts. I'm a bit nerdy in my family. We have a weather station in our backyard, and the hottest temperature I've seen since we moved to California was a couple of hours, it was in October a couple of years ago, was 116 degrees Fahrenheit. That's hot. Now, if you add 5 degrees Fahrenheit to that, that's 121 degrees Fahrenheit. That's really hot. My kids did try and fry an egg, although I don't think they were successful. So when we think about average temperatures, maybe a couple degrees, yeah, who cares? It doesn't matter. But you take those heat waves and you add a couple degrees, and that becomes concerning. When Claremont becomes more like Las Vegas, for example. And what's going to happen is not only will the extreme hot days get increased, but also the duration of those heat events. So this map is showing you this CalAdapt data. It shows you in the past, the 1950s to about 2010, and then model output running into the future, depending on how much carbon dioxide you emit. And it's showing you the number of extreme heat days over 99 degrees Fahrenheit. Goes from maybe 10 days up to, depending what we decide to do, 40, 50 days above 99 degrees Fahrenheit. So how do we adapt? We have to cool our cities. We have to take the places that we live, and we need to increase the reflectivity, and we need to cause shading. Trees are wonderful. We're so lucky to live in the city of trees. But you know what? Not all our neighbors have as much trees. And even within Claremont, there's inequity in who gets the shading from trees. Thinking about North Claremont versus South Claremont and some of our neighboring communities. There's also technology to increase the reflectivity depending on what the surface is of different materials. There's cool pavement movements, cool roof movements. We can also think about access to green space. These are all things that we have control over where we live that can help mitigate those extreme heat events. If we think about rainfall, average rainfall in Southern California isn't actually likely to change that much from year to year. But what is going to happen is we're going to get that rainfall in shorter, more intense storms. So in the past, maybe we've had 3 or 4 inches of precipitation during a 24-hour event. In the future, it might go up to 6, 7 inches. And those are going to punctuate longer dry spells. So droughts are going to get worse. So what do we have to do? This is just showing you the droughts, is that when we have that water, we have to retain it. So I think of it as a term I heard thinking about how other communities and places are thinking about resilience, is we have to turn ourselves into a sponge city. When that rain comes, let's not shuttle it off to the ocean. Let's capture it, absorb it, and get it back into the ground so it's available to us when we're in the drought. But again, thinking about the most important thing is that's implementation. And here I am thinking about it in terms of climate solutions, because we do have a pathway to solve climate change, thinking about it both in terms of mitigation, we know how to do it, and in terms of adaptation so that we're bolstering our vulnerable communities. And there's 2 ways that I think about it. I think about the people that we need, and this is just a small sampling. Basically, we need everyone. We need to think about everyone who has a role in it, and it can be done in our communities. We need to be in touch with our municipalities, with the government at all stages. Local government has so much power at our scale to actually make change. We need to think about it at the state, regional, federal government, international communities. We need to think about disruptors. And here, when I think about disruptors, it's people who challenge the status quo. People who say, well, just because I've driven to work every day, do I need to, or can I switch to other modes of transportation? Do we need to be doing it this way, or could we do this as well? Who ask the questions, because we need a radical transformation. We can do it, but we need the people who are going to lead it. And then educators, that's a personal one. We need people who are out there who are talking about it, who are climate literacy, who don't just put up a bunch of data and say, oh, as you can see, because you might not be able to see, right? We need people who are out there to think about these are solutions that might work. Let's have a conversations about which ones are right for you. We also, in terms of solutions, think about things we can do. Live longer. What does live longer have to do with climate? Well, it turns out a lot of personal actions that we can take to reduce our carbon footprint have co-benefits. 2 examples. 1, drive less. If you carpool, you get to spend more time with friends and colleagues and acquaintances. It turns out that having socially strong networks is one of the things to have longevity. If you drive less and you do other forms of transportation, if you ride your bike or if you walk, turns out those are great for you and it helps you live longer. It also reduces air pollution. Can you imagine if Los Angeles took all the gas cars off the road? It's not going to happen. I'm not advocating for it. But imagine how clean our air would be. We'd be able to see the ocean every time we went up into Johnson's pasture and looked out towards the ocean. We need to have a lot of conversations. Every time we talk about climate change, that's going to help shift people towards action. We need to think about transportation. We need to think about buildings. I don't find buildings very exciting in terms of having to go through and insulate, but those make a difference. If you change the structure on top and how much that energy is absorbed or reflected, it can cool the building and also require less energy. But I think something that's really important too is we need to think about the people that are controlling policies and regulations, and we need to vote. So that is something to keep in mind. There will be an election coming up, I've heard. And what happens in that election will actually have a very strong determinant on what the US does in terms of climate change policy. One reason I'm optimistic is I've had more conversations about climate in the past year than the decade before that. People are starting to feel it, people are starting to care about it, and we are making progress. And that is in part done because the government is putting resources into it. So I am actually optimistic about what's happening with climate change. So to sum it up, our climate is changing, but we control how much it's going to continue to change. It's our decision. The consequences are pretty severe if we do nothing. How do we mitigate it? Go towards a decarbon. We need to reduce, replace, maybe remove, but let's really thinking about reducing, replacing. To adapt, we need to think local, and we need to think about the things that impact us the most, and how do we build resiliency towards those. Cool a city and retain our water. Those are just kind of short phrases. There's a lot of other things that we can do. But most importantly, we all need to do something. If we do, it will cause a difference. I'm going to end there, but I will say I would love to continue this conversation. So I have my email up here. I'm also Branwen. I think I'm the only Branwen in California, so you can probably find me, and I would welcome talking with you more. Thank you.
Going to stop the slideshow now and go to some questions. We only have a few minutes, but we'd love to have your questions. If you're on Zoom, we're going to make the gallery view. You can activate your cameras and your speakers. Do we have questions from the audience here in the Louise Roberts room? Yes.
Let's say we get to net zero. How long before temperature starts to come down?
Okay, that's a great question. The question is, once we get to net zero, how long until the temperature starts to come down? It probably wouldn't come down. It would stabilize. The carbon dioxide we put into the atmosphere stays there for decades to centuries. And it also starts processes like melting ice. So the example I gave with the ice melting was when it got cooler and ice forming, but the same processes are occurring in the reverse. So Arctic sea ice is melting. We're probably not going to revert back to where we were. So it's really a stabilization, not a coming temperatures back down. To cool temperatures, we would have to take carbon dioxide out of the atmosphere for that.
Can you give us a thumbnail sketch about not taking the 65 million year scale, but the 600,000 year scale? How do we know what the average global surface temperature was? So where does that number come from?
Yeah, so the question was asking, how do we know what average temperature of our planet was on the 600,000 year timescale? And there's a variety of different climate archives. And so we have the ice cores. So we can measure the composition of the gases that were in the atmosphere, but we can also measure the properties of the ice itself. And we have these little bugs called foraminifera that live in the ocean, and they have a skeleton that's very similar to the one in the algae. They are very small, they're single-celled, they die, and then they layer in the bottom of the ocean. So we also have people that go out on research vessels, and they take cores from the bottom of the ocean, and they are layered of these little bugs, and you can measure the chemistry of those bugs. The primary tool is oxygen isotopes. So it's looking at the chemistry of oxygen, which varies depending on the temperature at the time that ice or those bugs were growing.
And if you know, how many data points is that average based on?
So for the last 600,000 years, it's on a lot of data points. As we go back prior to 1 million years, it starts going down. And then once you go prior to 65 million years, it goes down even more. So it depends on what climate archives are available to you. Those decrease. So trees can give us 2,000 to 3,000 years. And then you need to switch to a different type of climate archive. Lake sediments go kind of then bridge, and then you go ice cores. Ice cores can actually be pretty short. There's some tropical ice cores, Peru and the Tibetan Plateau, and Greenland can provide kind of shorter timescales. And then Antarctica and Greenland provide longer timescales. And then you kind of go into the sediments, and then they can provide longer timescales. So it depends on which type of material has been recording environment. We know more recent better, but really it's not that the average value we know it any better. We actually know the variability around that value better. The average value we're actually pretty good with. And often what we'll do is we'll actually present the value with the range and values around it, but those plots get really messy fast.
Final question? Yes, Peggy?
What proportion, you started your talk talking about transportation.
Mhm.
What proportion of the carbon dioxide source is transportation? So that counts cars and buses and airplanes versus all other sources.
Yeah, so the question was, what proportion of carbon dioxide emissions come from transportation versus other sources? And I have that figure. I don't know off the top of my head what it is, but it's significant. Even
More than half.
I don't know, because industrial processes are a lot. But if you also want to include into that shipping containers, shipping traffic itself is like 1%. So transportation is, I don't think it's over half, but it's significant. It's a lot. Yeah. And it's also one of the, some of it, planes are different, but some transportation, it's easy fixes, right? So picking your battles of the easy things first.
Thanks to Dr. Williams. Great presentation. Be sure to join us in the weeks during April, both in worship and during education time. And there are options to enroll in online activities and to, of course, participate in Earth Day here in Claremont. We hope you'll join us each and every opportunity. Thanks again to everyone. Enjoy worship today, and thanks for being here. Thanks.